800,000 actual cubic feet per minute with a 99.1% collection efficiency. Assuming an effective drift velocity of 14 feet per minute, calculate the required collection area. Okay, anytime you see an ESP problem with certain values given, such as flow rate, efficiency, area, drift velocity, you know you're dealing with a Deutsch equation problem. Remember, the Deutsch equation is simply the efficiency is equal to 1 minus e to the minus AW over Q. And so the solution is to rearrange that equation to get the term that we need. In this case, we're being asked to calculate A, the required collection area, and we turn that around by first bringing, algebraically, just simply bringing the exponentiated term over here, the efficiency over here, and now we can take the natural log of both sides. This becomes minus AW over Q is equal to the natural log of 1 minus eta, and then we turn that around. So algebraically, just something like this. Make simple sign errors. What I do is bring the 8 over here, bring this over here, take the natural log of both sides, and now multiply through by minus Q over A. Sorry, Q over W. Ahead of myself here. Should stick with what's pre-printed. And that will allow us to solve for the missing quantity A, plugging in the numbers. Be sure when you do this, be sure that your units are consistent. So if Q is given in cubic feet per minute and W is given in feet per second, convert one or the other of those two to get consistent units. We come out with an answer here of 269,000 square feet. Question 14 deals with a cyclone, and the design method presented in the text of Lappel and Shepard originally solved the cyclone problem 60 years ago, but that has remained effective for many years and thus is still accepted for use and is acceptable for use on a PE exam problem. So we're talking about a Lappel conventional cyclone as discussed in chapter 4. It has an inlet height given of 1 meter, a width of a half a meter. So we have dimensions of the inlet. We're given the standard air viscosity. Notice the units, metric, and the particles have a density of 1,100 kilograms per cubic meter. What is the cyclone cut diameter? And of course, the cut diameter is the key parameter for a cyclone that will allow us to calculate how efficient it is. Well, we start with the equation given in the chapter 4 for cyclones. But first we convert the inlet velocity. We calculate the inlet velocity based on the volumetric flow rate coming in divided by the cross-sectional area through which it flows. So that's the velocity. So remember your cyclone diagram. When all that volumetric flow rate is going through there, there is the height and the width, and that gives you an inlet area, and Q divided by that inlet area is going to be the velocity going into the cyclone. So once we have the velocity, we can plug it right into our design equation. Again, you have to make sure that your units are all correct. If you have mixed units here, you will get a mixed up answer. But in the units given, viscosity in kilograms per meter per minute, W in meters, VI in meters per minute, and rho P in kilograms per cubic meter, we're ignoring the density of the gas here in solving this problem. We simply plug in all the numbers, and we're going to come out with meters squared here. To the 1/2 will give us meters, so the diameter comes out, or the cut diameter comes out in meters, and we can convert that to microns by multiplying by 1,000,000. And after that problem, we'll come up to tip number 6. Always check to make sure that you're using variables with proper units. Sometimes some equations are empirical. They require specific units. That is, they were derived with certain assumptions or certain parameters with certain units already embedded in them. And therefore, when you use those kind of equations, you must plug in exactly the units that they call for. Other equations, like the Deutsch equation or like this equation, you can work with a set of consistent units. You can work in English units or metric units, as long as they're consistent and the units cancel out and give you something at the end that makes sense. So always be sure to keep track of your units. Okay, question 15. An ESP is treating the flue gas from a coal combustion unit, and it's achieving 98% removal of particulate matter. But then the power plant burns a new coal, a coal from another source. The efficiency drops to 93%, but the gas flow rate has remained exactly the same. So what happened here? The properties of the dust, properties of that particulate matter have changed. And that shows up in the fact that the efficiency of collection has dropped. Well, the area of the ESP didn't change. The gas flow rate, we're told, didn't change. So the only thing left in the Deutsch equation is the drift velocity. That's the only thing that could have changed, and that has been affected by some properties in this newer coal. So we can use this information to estimate the ratio of the new effective drift velocity to the old one. Let's take a look at the solution to that. We use equation 5.7 twice. That is, we rearrange the Deutsch equation for the new drift velocity like this, and for the old drift velocity. The only thing that's changed is the efficiency. Now, if we divide equation 1 by equation 2, the A and the Q cancel out, and we're left simply with the desired ratio, W new over W old, equal to natural log of 1 minus 0.93 divided by the natural log of 1 minus 0.98. Now, this is the ratio of two natural logs. It is not the same thing as the ratio of natural log of 1 minus 0.93 over 1 minus 0.98. Not equal to that. So don't make a simple algebraic mistake. Keep track of what you're doing with your calculator as you're punching the buttons. So this ratio is 0.68, about 2/3. That brings us to problem number 16.